It's a great pleasure to introduce Professor Dan MacLean, who is the head of bioinformatics at the Sainsbury Laboratory in Norwich. He grew up in and attended state school in Wigan in the northwest of England, going on to study biology at the University of Manchester. He has a PhD in molecular biology from the University of Cambridge and gained postdoctoral experience in genomics and bioinformatics at Stanford University in California. Dan is now an honorary professor at the School of Computing Sciences at the University of East Anglia. He has worked in bioinformatics and plant pathogenomics, specializing in R and bioconductor, and has developed analytical workflows in bioinformatics, genomics, genetics, image analysis, and proteomics at the Sainsbury Laboratory in Norwich since 2006. Dan has developed and published software packages in R, Ruby, and Python, which have a combined over 100,000 downloads. So it's a great pleasure for me to welcome Professor Dan MacLean to the Get Genome seminar. Thank you.
So hello everyone, I'm Dan MacLean, and it's a pleasure to talk to you today about how you might get some free computers for doing your bioinformatics analysis. So the main aim of my talk is going to be discussing options in open and free resources that you can use to get your genomics analysis done. So I hope to give you an overview of these and some ideas on how to move forward. So by way of demonstration, I will be doing some quick analyses on very tiny data sets, but I don't want you to get the wrong idea. The demos will be to show you how the resources work and explicitly not necessarily the best practice for any of the analyses. They'll be deliberately quick and dirty. Best practice is for another talk. Okay, so what do I mean by free? How are the resources I'm going to tell you about free? Well, they're gratis, to borrow from Latin. They're free in the sense of free beer. You can have them, but any headaches arising are yours to deal with. Some of them are completely free up to a point, and costs come in as you scale up. The rates are generally quite cheap, though when you do start to incur charge, and helpfully they can be paid for. At point of use. There's no need to generate a large capital grant. You can pay for these as operational expenses when you need to. None of them's perfect, and you need to pick your trade-offs. In particular, I want you to realize that bioinformatics is quite hard. It's a big set of skills, and you do need to skill yourself up to do it. Every data analysis is different, and each scientist is responsible for their own work. And that means that none of these solutions are one where you put your data in one end, press a big red button and the answer just pops out. You still need to become expert with the things the tools you'll use are doing to your data, as it'll be you, not the computer, that's responsible. Okay. I spoke of trade-offs. The trade-offs we generally have are quite easy to think about. Given these three features, cheapness, power, and accessibility, you can have any two. Picking two excludes the third, and thinking about them in those terms gives you a good idea about what you can do with each of the resources. Okay, I'm going to discuss three resources. First, AWS, Amazon Web Services, which is a raw data center-based solution. Then Galaxy, which is a graphical tool, and Jupyter on Google Colab, which falls in between both a bit. Okay, first, AWS. So, Amazon Web Services is a service created by Amazon to take advantage of the huge economy of scale they have when purchasing computers and building data centers. If they're building huge data centers and buying millions of computers to run in them, why not buy extra and rent out the bits they aren't using? That's the basis of it. If you need a temporary computer, you can rent it off Amazon. A completely blank computer with nothing on it, except a very minimal version of the Linux operating system. And this one is cheap. You could get a full analysis done for the price of coffee and cake, and there is a lot of power available to you. Companies like Netflix and Facebook use AWS for their own compute resource in their commercial products. You've used AWS computers before, but it is power user level stuff, so it's not the most accessible. And so when you do sign up to AWS and pick a computer type, which is something of a trial in itself, then you have only a command line to go from. If you know what you're doing, are you prepared to climb that hill, then it's a great solution. Okay, and that's all I'm really going to say on that, because I want to focus more on the more accessible options. And now we'll go straight to the other end of the spectrum and we'll look at Galaxy. So Galaxy is a publicly accessible web tool that allows you to upload your own data and run it through common bioinformatics tools. It is fully point and click, and it is publicly funded on both the development and hosting side. This means there are numerous instances of Galaxy around the world. It exists at different web addresses, and there are differences between the different instances. Specifically, the set of tools at each is different, though they do overlap. The main Galaxy project page has lots of information about them if you want to try and work out which one's best or nearest to you. Okay, so I'll do a demo. I'm going to run through how to use it briefly for a couple of use cases. First, I'll upload some sequence reads and do a QC. This will just be a small data set. Second, I'll run a longer assembly pipeline. This will be a much larger PacBio data set, but still relatively small. Okay, this is the main Galaxy front page at usegalaxy.org. We can see 3 vertical panels. That center one is where the main interface will pop up. On loading, there's nothing for it to do, so there's a set of adverts and acknowledgements right at the moment. The guy you can see is James Taylor, who with Anton Nekritenko founded the whole Galaxy project. The rightmost vertical panel is called the history. This is where your data items, the data that you upload, and the ones that get spit out of computational jobs appear. They appear as little boxes. And the leftmost panel is the set of expandable menus that you can navigate through to find the tools and things that you need. So let's have a quick look at getting some data into Galaxy and running a simple job. So starting with the upload of data from your computer, we click the upload button on the left and are presented with that dialog box. The job queues and eventually runs, and when it's done, we see it appear in the history as a new item. When it's green, it's ready to use. We can click on the history item and on the eye icon to get a quick preview, and we can see that these are indeed sequence reads. You can only see the top of the file really. So I can now pick a tool to use from the left panel. I'm going to do some quality control. So I'll pick that subsection and I'll use FastQC for a quick check. There it is. When I click the tool, its options appear in the center panel. The first option is usually which dataset you want to work with. Galaxy has a concept of types and will only let you select a suitable input, which here is the sequences I've uploaded. I'll only use defaults for this and click the Run Tool button when I'm ready. Once that's done, the jobs are submitted to the computers that Galaxy sits on, and they stay grey while the job is in the queue. They go yellow while the job runs, and when the job's done, they'll turn green. Shouldn't take a second. This is a very small data set. There we go. On the green, we can inspect the output. So we can click on the history items, click the eye icon, and we can see the FASTQ reports of the very small data set that I've analysed. Data view is a bit squashed here just because of the screen I'm working on. If you've got a bigger screen, or you can choose to lay it out how you like. We can see that these reads, because they're a very small random set, haven't come across in a great quality. The next level in Galaxy is its workflows. These are really useful if you want to build large pipelines for reuse or for sharing. This is the best bit of Galaxy really, as it's the feature that lets you make the computer work for you. When you click the workflow in the left pane, start the video, you can create a new workflow that presents you with this design space. Selecting tools from the list on the left puts boxes representing them in the main pane, and you can start to link inputs to outputs from each tool. So here I'm adding Minimap and MiniASM. I'll link these together, link the output from one into the other, because I want to do assembly and alignment with them. And because we're going to do PacBio data, this usually comes as BAM files. So to run these tools, we'll need to extract the reads. So I'll add a read extracting tool. There we go. And when we're happy, when we've built a pipeline that we like and all flows together nicely, we can run it or save it for reuse. Here, I'll reload a saved workflow for the task that we're running. And the workflow appears in the main panel. There we go, that's one I built as a demo before. So I'll select, we press run rather. It loads up the workflow in the main panel, and I can select a data set from my history. The only one that works is this BAM file. I can click run, and run will submit all the jobs into the history. You can see them appear on the right as grey boxes, each of which will run in turn when its dependencies have already run. So, and that's that. So Galaxy is pretty useful for doing analyses. Major disadvantage really is that the tool set is fixed, although the tool sets are pretty broad. Okay, so it is possible to get your own private version of Galaxy, though you'd have to install it on your own machine or AWS completely from scratch, so it creates admin hurdles. There are also versions, containerized versions, so packaged versions ready to go that could be installed on things like the Anvil service, which is somewhat curated and managed bioinformatics cloud solutions with different streams for commercial and academic users. So these could be worth a look depending on your personal circumstance, what you specifically need, if you really need to be able to add your own tools and things into Galaxy. Okay, and the next resource I want to talk about and spend most time on really is Google's Colab or Colaboratory offering. So Colab is another cloud service that's based on top of Google's vast hardware. So generally all you need to access it is a free Google account, and it scales up when you put in your credit card. You can get access to large amounts of RAM, disk space, and helpfully it links to your Google Drive, making uploading, etc. much easier. Colab has access to GPUs as well, meaning this is a favourite place for people to do AI and ML projects with. And Colab is probably the most equitable mix of our cheap, power, accessible matrix. The power can come if you pay for it, and a lot of the difficulty of dealing with files and uploading or connecting to the internet is reduced by Google providing nice integration with a GUI for file operations. You do still need some knowledge of command lines though if you're going to get anything done, but not too much system admin knowledge, which is great. I mean, there is one catch. The computer is completely temporary, by default at least. After about 12 hours of use, or if you close your browser, the computer you're connected to, or it's actually called a runtime in Google's jargon, resets. And this is why connecting to something like Google Drive is crucial. Google will sell you more time and more, as well as more power. If you look into Google Cloud Marketplace, you can start to look for paid solutions that might scale to what you need, but you will find the default offering very, very useful. Okay. The heart of Colab is the tool called a Jupyter Notebook. This is just one type of something called a literate programming document in use. There's lots of these systems in bioinformatics today because almost all bioinformaticians worth the salt use literate programming as a daily tool for recording how they've done the work. And you can see in the picture an example. A literate computing document is one that mixes normal text and pictures with computer code. And you can see that here. In the top half of the picture, you can see a text description of what's going on, this section. And in the bottom, you can see some code that implements it. And the results get piped back into the document. So it's a kind of reactive live document you can rationalize, record, and execute with. And it has its own GUI for working with lots of stuff to do with it as well. So you don't have to know just code, though you can work with it on a code-only basis. Okay. Because of the transient nature of the runtime, you need to connect to Google Drive and stay organized. As I said, you can't rely on the computer being there and save your notebooks And you should save your notebooks and files to the persistent Google Drive that you have. It is easy to link to the drive. It just takes a tiny bit of code. The next thing you'll need to be able to do is install the software you need to use. This is greatly simplified by using tools known as package managers. So packages are bundled up bits of software that know all about their dependencies. That is to say, which other bits of software they rely on. And package managers can read that information and install all upstream components for you. The figure here is a graph of dependencies for a typical Python package. As you can see, it's quite complex, and navigating it manually is quite a headache. Package managers are a bit of a lifesaver, so you want to get to know how to use those. And there are 4 package managers I'm going to introduce you today. apt for system-level software, pip, the standard Python one, and conda and bioconda, which are more for specific bioinformatics tools. So the apt package manager is the system package manager on the operating system used on Colab. So you use apt to install system-level packages. So remember, the computer is pretty minimal when you first get it. So if you need to extend its built-in capability, apt is the way to go. You'd use this for programs that do everyday stuff like zipping files with gzip or downloading with wget. You'd also use it for installing programming languages beyond the basic Python and Bash you get by default. There are a couple of examples at the bottom there, which when entered in a Jupyter code cell, will install gzip and wget. The next one is pip for Python packages. So Jupyter's multi-language, but Python comes first, so this is a useful one to know. A lot of what you can do with Python isn't in the language, but externally managed packages. For example, BioPython, which provides a lot of useful bioinformatics-related methods. It's really useful to know how to use pip. The next 2, conda and bioconda, are very powerful and widely used package managers in bioinformatics. These can install packages in any language and manage dependencies and conflicts using something called environments, which allow multiple versions of the same software to coexist if you need that. And quite often you will if you're working with legacy software and you need the latest methods in a new version of a particular package. Bioconda is a specialization within Conda that contains over 7,000 bioinformatics tools, and it's maintained actively by the bioinformatics community. All the tools are easy to install and run just as they should. Virtually every bioinformatician uses Conda and bioconda in some form or other. Installing these is really straightforward. You can see these installation instructions here. So basically in the first panel, we download the Python package that installs using pip, then load that and run the function that installs conda for Colab. Note that a message telling us the system crashed is normal. This process needs the computer to restart, so if you try this and it says it's crashed, it's fine. In the second panel, we configure conda to know about the bioconda channel, where the bioinformatics tools are. And in the third channel, we go ahead and install the actual tools. Here, SAMtools, Blast, and Minimap. Sorry, FastQC, SAMtools, BCF tools, and PWA. My mistake. One thing to remember is that you'll need to do this every time you start a new runtime. Remember, the computer expires after a while, so it needs rebuilding. Okay, so I'm going to do a demo again, and this is the workflow I'll follow in the Colab Jupyter demo. Roughly, we'll set up the machine with what it needs. Then we'll do a fast QC to check some reads that are prepared, and then call some variants using those reads. The origin of the reads doesn't really matter for a tech demo, but they come from E. coli. Okay, start the video. There we go. So here we can see the Colab Jupyter notebook. The main panel is on the right, and the file browser that makes things a little easier is on the left. The notebooks are auto-saved, so the first thing I do is change the name. Then I'll start adding normal text. Remember, this is supposed to be a live analysis document, so I need to set out my intentions and assumptions and hypotheses before I start. This is a great place to put a Go rep for your work if you're familiar with those sorts of ideas. Note how the editor auto-formats. I'm typing in a mini format called Markdown, which tells the text how to look or how to structure itself. And when I save the cell, it knows how to render the text. I can use the menus above the cell if I want, or if I need to add or delete new cells. Okay, as you can see, I'm given a pretty full description of what I intend to do. And I can add a new code or text section if I like. If I accidentally add one, I want to delete it, there are options for that in the little menu that pops up. So there we go. So I've done my outline, and I can move to the next step and describe that before I do it. So I'll be installing Conda using the Python package that Google provide. This much text might seem pedantic, but it is a kindness to your future self. Computer code is often much easier to write than it is to read, so having the natural language there is a big help for reproducibility and reusability, even if you're only helping yourself a couple of months down the line. Okay, so here we add the code to install the Colab package. Takes a second, and when I'm ready, I can press the play button and the code will execute. Any messages appear underneath, and when the circle stops spinning, the notebook is finished and that command can move on. There we go, that's done. So I can now move on, happy that that's finished. Do you get a message about the kernel restarting, which causes pause for a second, but when I can add new text boxes, I'm ready to go. Okay, so the next thing I want to do, having installed Conda, is get access to my data, so I'm going to mount my Google Drive. Okay, so I'll add the description for that. And I'll leave a little memo for myself. And having done that, I can add the actual code and run that. So all the code that I type in here is written in the earlier slides. So if you need to get at that, you can just look at the slides. Okay, so now I actually mount the drive, and I specify the mount point of the drive. This is the place where the file system will stick the Google Drive on, and it can be accessed from. It's the folder in which it appears, basically. Okay. It asks for some permissions, and I accept them all. And when that runs through, takes a second. There we go. Tells me that it's mounted, and we should see, yeah, the folder on the left here appear, a folder called Drive. Oh, sorry. Skipping about, sorry, put the wrong thing. Okay, so the next step then is to extract the read data in my Google Drive from the gzip format that I received it in from my sequence provider. So the extracted version I always think of as temporary data, and I don't care if it gets deleted, so I'll let it extract into the runtime. And because it's gzipped, I'll be able to extract it with the tar command. That's what I'm writing here. Okay, so now I can add the code that will extract the reads into my local disk. Note the start of the path to the file, the compressed archive file, the tar file, the gzip file, is starts with the mount point that the previous command told us about. That's where we find that folder. Okay, that's all we should need. And I can press play, and it starts to extract. Cool, looks done. So I can move on. And I can start to install the tools that I need now that my data is ready. I intend to do that from Conda and BioConda. Which we do. We know we've got Conda installed, and we can tell Conda about the bioconda channel. You can think of each of these things as a bit like an app store. So we're just configuring app stores to install app stores in a way. And I'll list which tools I intend to use and outline my analysis beforehand. Basically just a bit of experimental design and planning. Okay, I can add my code. And then I can configure Conda to add all the channels that I need. With the channels added, I can actually do the install of the software with the Conda install command. Warnings like this are normal. All it's telling me is that it actually already knows about Conda Forge in that one. But warnings aren't usually something to worry about. They're different from errors. So we'll proceed, even though it's warned us. We don't worry about it too much until it actually catches up with it later. So installs take a very long time, and I've sped this section up by about 20 times in the video. So if it seems to be taking a lot longer, if you try this, than it does in this video, don't worry about it. There's a lot of stuff to install here. You can see it's working quite hard. Good. That took about a minute of real time, a minute and a half. Okay, so then with the software installed, I'll explain the next step in the document. So I'm telling myself here really, that I intend next to run FastQC. This is the next step in my analysis. We looked at FastQC in the Galaxy bit. FastQC just checks the reads for quality. So we'll ask it to run here on all the read files that we extracted. So everything in the subfolder. If you notice on the left, that's the folder that was created by the tar extraction command a second ago. Again, the output goes, the system messages go into the box underneath the code. This takes a little minute as well. It's running through each file. Each file is very small, really. So it's running through quite quickly. There we go, it's done, 27 seconds. And if we open the file here, we can see that the output has appeared in the subfolder. And the output happens to be a HTML file, not a text file. So we can't view it within the Colab book. So I download it using the GUI to my computer, and we'll have a quick look. There we go. We can see the FastQ output, FastQC output rather. And you see that the reads are in pretty good shape this time. These are decent reads to do an alignment with. No real issues. The couple of orange items there are just because it's a small file. Okay, so the results are good. So with the result, I'll record that into my document and record also my decision based on that conclusion in this next cell. So it looks good. Okay. So the next step is to record my plan for the next step, which is the alignment. I intend to do that with BWA. Okay, so if I'm going to do BWA alignment as well, this works by first creating an index of the reference genome. This just makes the alignment a bit quicker. Then we can actually align the reads and we get something called a SAM file, but that's disordered. So we need to sort it to be able to use it efficiently and create a compressed binary version, so a BAM file. And then we've got that, we can run alignment checks on it. Okay, so let's start the code. Okay, so the first is the index. So the reference genome is in my Google Drive because that's something I want to keep and access over and over. So now I need to pay attention to the long paths to give it the name of the position of the reference genome FASTA file. And then I run that. Good, that just takes a few seconds on a short E. coli reference. And the next step is to do the BWA mem alignment. Other aligners are available if you prefer them. Use BWA mem in tutorial context mostly nowadays, but just because it's fast and there's a simple command line interface. There we go, we give it the reference genome and the path to the reads in the subfolder to which we extracted them. And because this is a paired end alignment, there's two sets of reads to go in. Okay, having told the computer about that, we can press run and the system messages go to the screen. Oops, that's a mistake. Oh, that's not system messages, that's actual output. So I've forgotten to provide the output file. So I can stop the process by hitting the stop button as it runs. And then I can edit my command and give it an actual output file this time. So I'll release the text format is called SAM format. So I'll pipe it into a SAM format file, or at least a file with the SAM extension on it, so I know what it is. Okay, so they've got the system messages this time. Doesn't look like we're getting any output data, which is good. There we go, the alignment finished. 27 seconds it's telling us. It is a very small data set indeed. So with the next code, we can run through the SAMTools steps for processing and sorting the alignment. So I'll first turn the SAM file into a BAM file. That shouldn't take very long at all. Yep, that's done. And next I will sort the BAM file. It sorts all the reads by alignment position so they're easier to find in the file. Again, that's quite quick. I've got a sorted BAM file now. So now I can do something a little more interesting and check the quality of the alignment. So I'll do this in the SAMTools framework with flagstat, which is just gives you a rough idea of how well everything aligned. It's not a thorough inspection, but it gives you some headline statistics. There we go, and there are the output. There are the statistics from flagstat, and you can see that almost all the reads mapped primarily, so in just one place. So that seems like a decent enough alignment for us to move on with. So again, this is a result and a decision point. So in my live document, I record that and say that I'm going on to my next planned action. Okay, so moving on to the next step, we can start to try and find the variance in the reads relative to the reference genome. Again, this is a new analysis step, so I'll record it in the text box and I outline my plan. So there are just 2 steps. So I'm going to create a count of all the bases aligning to each point. So this is called a pileup. And then you can scan the pileup to find out where the aligned bases at each position differ from the reference. So to do this, I'm going to use BCF tools. Okay, so then we enter the code to run BCF tools. So this is going to be the pileup to start with, and the options for that. These are all in the manual for BCF tools, so I won't bother explaining them here, but basically they're just saying, create me a pileup. It needs to know the path to the reference genome, so it knows what the reference allele, reference bases are. So I'll enter here. And there is we provided our sorted BAM file from the last step of our alignment to run on. That shouldn't take long. Good, 20 seconds or so. And then the next step is to call the actual variance with the BCF tools call. To do this, you need to tell it a little bit about the ploidy and the expected input. But really all we need to do is pass it the pileup file. Okay, hit go. And you see these files starting to appear on the left as we go. That only took about 7 seconds. So now we should be able to check the output with flag stats. Okay. Finally then, I can record my result and have a quick look in the variance file. So this isn't a very in-depth examination. I'm just going to have a quick look because this is a tech demo. It's worth pointing out as well that this is a completely unfiltered set of variants, and variant calling is very false positive rich, shall we say. So it's often the case that you have to do some filtering and completely skip that step out here. We'll just have a quick look. Code, please. Okay. So I can do this just by using the standard tail command, which lets you look at the bottom of the file. Here I'll look at the bottom 20 lines of the file. And there we can see very nicely indeed that we've got the SNPs and indels. So the left-hand columns are the reference chromosome and the position, and the 2 columns in the middle there are the reference base and the alternative base. And we can see there are lots and lots of differences. If I want to bring this particular file to my own computer, I can do that by downloading it, or I can save it in my Google Drive using the file options. Good. Okay, so that's Colab then. So the other great thing about the Jupyter Notebook, I suppose, is that this entire document can be saved. You can save the whole Jupyter Notebook, and it's a lab book. It's a live record of the decisions that you made as you were going along, and the way that it resulted in data or interpretations. So if anybody asks you, or you need to provide methods, then this is exactly what you did, which often gets overlooked in bioinformatics. So it's really why a lot of good bioinformaticians are turning to these sorts of documents to record the daily work. Okay. Good. All right. So that's all I wanted to tell you about, really. In summary, there are free computers available for bioinformatics analysis, and at least 3 of these are the Amazon Web Services, the Galaxy framework, and the Colab course. Each has its trade-offs. You've had a quick view through each. But I would recommend Colab as a starting place for open and reproducible science, bioinformatics especially. And it's probably the best overall for recording your work and the best value for money. Okay, thank you for listening. The only acknowledgements I have are to the people who pay me. I work at the Sainsbury Lab for which is funded by the Gatsby Charitable Foundation. Thank you for your time.